So I want to pick up where we finished last time. So we were talking about the method of undetermined coefficients. And I hope I didn't make it sound overly complicated, because I think by the time I went through and said, oh, let's walk through an example, I feel people may have said, like, oh, this seems very complicated. But it's actually a really beautiful idea. So what's our setting? So we have a nice ordinary differential equation. It's really nice. Constant coefficient. It's linear. And we have an f of x. And f of x is nice. Now you might say, how do you know f of x is nice? Well, it says it right here. It said it's nice. And of course, you have to say, well, what does nice mean? And in this context, nice means it's something that comes out of a constant coefficient linear homogeneous differential equation. So nothing very surprising. Things like powers of x to the whole positive number, things like exponential functions, things like sine, cosine, a combination of those things. Those are nice. And then what we do is we go through, there's a couple of steps. The first step, well, we find the homogeneous solution, which we've done before. So step one, we should feel pretty good about this. We like this step. This is a happy place for us. We know how to do this. You know, it's like, oh, okay, you set f of x equal to 0, you turn it into a polynomial, you find the roots. Once you have the roots, you have the function. Then we come to step 2. And step 2 says, now we're after the particular solution. And the thing is, in this really precise setting, we actually have a very good sense of what the particular solution looks like, up to some coefficients that we have to figure out. This is why we call it the method of undetermined coefficients. The idea is we know what the particular solution looks like. We know what yp looks like, other than we don't know what the coefficients are. So now, why do we say we know what yp looks like? Well, we can write down what the form is. So how do you do it? You take each part of f of x. Now, when we say each part, we mean if you have several things being added together, each piece that's being added is its own part. Okay, so that's what we mean by take each part. And now, if I see a part, that's going to be a piece of our particular solution. So, for example, over here, where we have a problem where 5x squared e to the x. So here, x squared e to the x is a part of our particular solution. We don't worry about the 5. That's a coefficient. The coefficients we are going to have as something undetermined. Now, if it happens to have x to a power attached to it, make sure you go down all the way. So if it's x squared attached to it, also have the part where there's just x, also have the part where it's just 1. So work your way down. If you have a sine term, make sure to put its cosine mate. Same thing, if you have a cosine term, make sure to put its sine mate. And with these two, you basically have what y to p looks like, other than there's a little caveat. That's the third bullet point. And the third bullet point says, okay, we know what y to p looks like. Let's just compare it to what we found in step 1. If there's any overlap with the functions, that's a problem. We got to get rid of the overlap. And so what we do is we do our bumping up. So when we talk about our phrase here, bump up, what we really mean by this is multiply by the right power of x. Now, usually it's just 1, but it just depends on how much overlap there is. So that's what we mean by our bump up. So step 2 is write down what the particular solution looks like. Up to, we don't know what the coefficients are. The third step says, okay, now that we know what our answer looks like, we just have to find the coefficients. And the way we do it is we take our answer from step 2, plug it into our differential equation. So we plug it into our original differential equation, and then we gather. We gather all our coefficients together and say the coefficients on the left have to match the coefficients on the right. This sets us up with a system of equations and lets us solve for our coefficients. Once we have our coefficients, we have our particular solution, and life is good. So that's the idea. So we're going to do a little bit of practice. I know we did some practice last time. We're just going to do a little bit of practice today. we're going to start by focusing on step 2. Because I think that's, once you have the idea in step 2, step 1 is very automatic at this point, we hope. Step 3, very mechanical. Once you do a couple of them, they all go the same way. So, any questions on what we have here for the method? This is good? Looks good. All right. Now an example. So, find the form for the particular solution for the following ODE problems. ODE just shorthand for differential equations. And you do not have to explicitly find the coefficients. So again, we're just focusing on step 2. We're not doing step 3 at this stage. Now you'll notice something about all 3 of these problems. Namely, all 3 of them have the same f of x. So that's interesting. It feels like we're doing the same thing 3 times. But perhaps there's a moral here to be told. And so let's follow through and see what happens. So suppose we haven't done step 1 yet, because we can do step 2 and tackle the first 2 bullet points up to the bumping. So let's suppose we haven't done the bumping, and we say, okay, what should y sub p look like? So our generic y sub p. What should it have? Well, what do we see? What's our piece?
5x.
Yeah, we have that 5x squared e to the x. We don't worry about the 5. So it should have something x squared e to the x. What else? Oh, whoops, that should be 2x. Yeah, I'm sorry. But yeah, we should have something x e to the 2x and something e to the 2x. Why? Because we're doing our first bullet point here. Anything with the lower power of x. So if I have x squared, I should have x, I should have 1. So I have to go all the way down. All right, so that's what our generic y sub p should look like. There's no sine cosine pairs we have to worry about here. So the only thing left to do is worry about bumping. Do we have to bump? And for that, we really need to look at our homogeneous solution. So let's start with part A. So we have y double prime minus 4y prime plus 3y equals 0. We're doing the homogeneous part. Translate that into our equation for r. What does it become? R squared minus 4r plus 3 equals 0. Does that factor?
Yes.
How? R minus 3, r minus 1. So in this case, our complementary solution is some constant e to the 3x, some constant e to the x. Now we say, okay, so the pieces here are e to the x, e to the 3x. Come up and say, is there any overlap? In other words, is any of the 3 parts here matched with any of the 2 parts there? No. So do we need to bump? No. And therefore, that is the right y sub p. So for this one, y sub p is just the same. ax squared e to the 2x, bx e to the 2x, c e to the 2x. All right, that's part A. Good. That's not so bad. Now, part B. All right. So, y double prime minus 3y prime plus 2y equals 0. In terms of the r, what does that become? R squared minus 3r plus 2 equals 0. Does that factor? R minus 2, R minus 1. So what does our complementary solution look like? C1 e to the 2x, because you have a root of 2, and C2 e to the x, because you have a root of 1. All right, so now what we do is we say, well, let's look at our generic y sub p and our complementary solution and ask the question, is there any overlap? Yeah, they both have e to the 2x. Okay, so if there's overlap, what do we need to do? Bump. Now, which term do we bump? Yeah, all of them, because you might say, well, look, if I bump this one, whoops, that's already accounted for, so I got to bump that one. If I bump that one, I got to bump that one as well. So anything where there's e to the 2x, all those get bumped up. So our particular solution, ax cubed e to the 2x, bx squared e to the 2x, cx e to the 2x. And there we go. All right. Well, that's 2 down, 1 to go. Part C. Y double prime minus 4y prime plus 4y equals 0. In terms of r, what does that give us? R squared minus 4r plus 4 equals 0. Does that factor? Yeah, it's r minus 2 squared. So what's our complementary solution look like? Constant e to the 2x and c2x e to the 2x. Now compare. Do we have any overlap? Yeah. How much do we have to bump? We have to bump twice, right? Because there already is an x e to 2x, and there's also an x e to 2x. So we've got to bump up twice so that there's no overlap. And so here we have that our particular solution would be ax to the 4th e to the 2x, bx cubed e to the 2x, and cx squared e to the 2x. So you'll notice, even though all three of these problems have the same function f of x, for the particular solution, they actually have slightly different forms. And the reason is, in each case, there was a different amount of overlap, so we had to account for it in different ways. So that's why we have to be careful. All right, good. Well, now that we've had that warm up, let's try something a little bit more. Determine the appropriate form for a particular solution of the differential equation, and it's written there, d squared minus 4d plus 5 times d minus 1 times y. Now remember, whenever you see a capital letter D, that's just a shorthand for saying you take a derivative. That's the differential equation, equals 3x squared e to the 2x sine x minus 7 cosine 4x plus 5x to the 4th e to the x. Good news, you do not need to solve for the value of the coefficients. And we will see why that's good news in just a few moments. All right. Well, where do we begin? Okay, finding the complementary solution. So we start with our differential equation. Now we could have, by the way, been given this differential equation in terms of like, y triple prime, something y double prime, something y prime. This way is kind of, they were being nice to us. Because in this notation, it's really quick to switch to our R notation in terms of the polynomial. The rule is D becomes R. It's really cool. So this becomes r squared minus 4r plus 5 times r minus 1 equals 0. All right, so now that's good. Do we know any of the roots? 1. Yeah, that's pretty easy to spot. Okay, we'll come back to that and talk about the function. What about this other one, r squared minus 4r plus 5? What can we do there?
Yeah, you're going to need the quadratic.
Someone says we need the quadratic formula. Yeah, it's hard to factor that one. Now we could also do completing the square. After seeing how students did the quadratic formula in the past exam, I'm a little bit nervous. But maybe it's good that we practice it a little bit more, right? Okay, so let's remember the formula. So it would be, how does the formula go? It's negative b plus or minus square root b squared 4ac, all of that over 2a. Okay. Now, 16 minus 20 Negative 4. Square root of negative 4, we write that as 2i. And note that when I divide by 2, I divide everything by 2. So the 4 over 2 becomes 2 plus or minus I. All right, so let's talk about our functions. So the r equals 1. What function will that be in the complementary solution? E to the x. Okay, 2 plus minus I. What will that give us? E to the 2x cosine and E to the 2x sine. So when you see complex roots, you get pairs, sine, cosine pairs. All right, so there's that part. Hopefully there's enough space for our answer. Now, that'll be fine. All right, so let's write it down without worrying about the bumping. And then if there's any bumping, we'll rewrite it. So there's 3 pieces here. Each piece, we're going to go through it. All right, so our generic y sub p, we'll start there. That's pre-bump. All right, so the first piece, don't worry about the 3. Write down the function. So there's a x squared e to the 2x sine of x. What else do we need? Sorry, what? We need a cosine, right? Because sine, cosines, they come in pairs. So b x squared e to the 2x cosine of x. Anything else? Yeah, see how we have an x squared? We got to keep going down in the powers. So next we'll go cx e to the 2x sine of x. And then what? Yeah, dx e to the 2x cosine of x. And then? Yeah, e to the 2x sine of x. And then? F e to the 2x cosine of x. And now you're like, I'm glad we don't have to solve for the coefficients because we only have one term. Next term, cosine 4x. All right, what do I need? I need a cosine 4x, right? If that's a piece, I just write down, okay, g cosine 4x. And then someone said, you also need the sine because they go in pairs. Do I need to do anything else with this? No, there's no powers of x, so that stops. Are we done? No. One more term. All right, so what do we need? Well, we have an x to the 4th e to the x, so x to the 4th e to the x. Anything else? All right, we need an x cubed e to the x. Anything else? An x squared e to the x. Anything else? An x e to the x. Anything else? An m e to the x. Anything else? No. That's it. We're done. So, what do we have? We know that this is what yp looks like. Pre-bump, we haven't actually gotten the right yp yet. Up to bumping. So if we just figure out what, I think there's that 13 symbols there? Yeah, we just have 13 things to figure out, and then we'd have it. Great. Great. But now the question, do we have to bump? Well, do we have any e to the x's? Yeah, we have an e to the x. But we don't just have to bump that e to the x. Which e to the x's do we have to bump? All of the e to the x's here. Now, if there was an e to the x sine x, we wouldn't have to bump that one. But all these e to the x's, so all of these get a bump. Okay, so we're going to have to do that. Do we have anything that looks like e to the 2x cosine x? Yeah. So what does that mean? All of that gets bumped. So, because we got to work our way up. Now the good news is we don't have to bump those two terms. Okay. So, now we just have to be patient and say, look. Now notice we only have to bump up by 1 power of x in both cases. So it's not so bad, it's just a matter of rewriting. Now you might say, Steve, shouldn't we have seen it beforehand? Yes, we should have. But, you know, live and learn. So you just recopy everything. Everything that's highlighted gets an extra power of x. And you can actually see ahead of time. It's like, okay, we see that there's an e to the x, so we should have anticipated a bump. But that's okay. We don't mind writing. It gives us practice. All right. Sorry, I don't feel like I'm giving enough commentary here. And he's rounding the corner. He's halfway there. He's almost done. Wait, no, he's not. He has a whole nother line. All right. But that's how it goes sometimes. So, all right. So the moral is, I think if you can follow along with this example, you can probably do step 2 of any problem. Because this really shows you what happens. You got your sines, cosine pairs, you got your powers of x, you made sure you found all the lower powers of x, we checked for bumping, we bumped everything, and so we're good. We're good. All right. Whew. Catch our breath for a second there. Any questions on this one? Yes, I see a question.
I have a question. What if it just bent? Oh wait, never mind.
Okay.
Sorry.
No problem. No problem. I like it when people answer their own questions. It's a great sign. It's good. It's good. All right. Oh, there is another question. Okay.
How do we come to this guess that it's of this form, like this YP?
This one?
All of it. Like, how did we come to the guess that it's going to be of this form?
Well, so you'll notice certain things. So the question is, how did we get to this guess? So you'll notice how this part had an x squared e to the 2x sine of x. So he said, okay, we'll start with that block. And that'll be a piece. And now there's 2 rules that you need to remember. If there's a sine, there's a cosine pair. So that says, oh, you also have the same thing where you place sine with cosine.
Why so?
Sorry, what?
Why is there a sine and cosine pair?
Well, because roots come in complex pairs. And so you have to remember that the reason that this all works is ultimately we're saying these things look like solutions to linear constant coefficient ODEs. And in those constant coefficient linear ODEs, sine, cosine come in pairs. And because complex roots come in pairs. So we said, okay, sine, cosine has to come in pairs. And then anytime there's the power of x, you have to go down. And the reason that we have that is because if you think back to constant coefficient linear homogeneous ordinary differential equations, the way we got powers of x's was repeated roots. So what was happening is, oh, this is a repeated root, so I have to have all copies of that root, which is why we go down. And so once you understand that drives everything. So this cosine 4x, that said, okay, you have that piece, and then you have to have the pair. The x, the 4th e to the x, all right, you have this piece, and that determines everything here. So essentially, it's these 3 pieces said, okay, those 3 parts are going to be part of my solution, but then my other 2 rules force the other pieces to fall in place as well. So that's how you figure it out. Okay. Now, let's actually do something which involves step 3. One last practice, and we'll move on to today's topic. So give the general form for solutions of y double prime plus 4y prime plus 4y is equal to 18 e to the x plus 8x squared. All right. Where do you want to start? YC. Okay, so we're finding the homogeneous part. Y double prime plus 4y prime plus 4y equals 0. What is that in terms of our characteristic polynomial? R squared. 4r plus 4 equals 0. Does that factor? Yeah. What does it factor as? R plus 2 squared. Which means that our roots are -2 and -2. So what does our complementary solution look like? C1 e to the minus 2x and x e to the minus 2x. Okay. All right, now we come to the second part. Step 2, if you will. So we focus here on our f of x. That's the right-hand side. And we say, okay, what's our form for y sub p? Well, let's not worry about bumping yet. We say, okay, y sub p, we see an e to the x. So what will we have here? A e to the x. We see an x squared. What will we have? Bx squared cx d. We have the x squared, so you got to work your way down. Now, fingers crossed. Let there be no overlap. Please let there be no overlap. Please let there be no overlap. Is there any overlap? Yo, woohoo! Yay! Okay, good. We don't have to bump. No bumping required. Nice. All right. So this is the right form. Ha 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 ha. Okay. Now, what to do with this? Well, we're going to take this and plug it into there. So we're going to plug it into our differential equation. It is a solution. So what will we have? Well, we'll have that 18 e to the x plus 8x squared is equal to this particular solution, yp double prime, plus 4yp prime, plus 4yp. So I'm plugging this y sub p in. So I really haven't plugged much in yet. I'm just saying, yeah, plug it in. And it works. That's because it's a solution. So that's a e to the x plus bx squared plus cx plus d double prime plus 4 a e to the x plus bx squared plus cx plus d prime plus 4 times the function a e to the x plus bx squared plus cx plus d. Now I should say you could somewhere on the side just say, okay, here's yp, here's yp prime, here's yp double prime, and feed it in. We're just doing it while we go through. All right, so let's see if we can do this in our head. Second derivative of a e to the x. A e to the x, nice. It's one of the reasons we like e to the x. Second derivative of bx squared. 2b? Or is it not 2b? Yeah, it's 2b, yeah. I can't resist it. It's too good. Second derivative of c times x? 0. Second derivative of d? 0. Okay. Plus 4. First derivative of a e to the x. A e to the x. First derivative of bx squared. 2bx. First derivative of c times x. C. First derivative of d? 0. It's a constant. And then the next part is just copying, because they're not doing any derivatives. It's just the function again. A e to the x plus bx squared plus cx plus d. All right. So this is us plugging in y sub p into the left-hand side and taking our derivatives. Okay, what's the next thing we do? Do you know? We've got to find coefficients. So what do we do? So what we should do is we should gather. So let's gather by functions. E to the x. All right. So we're going to group everything that's attached to an e to the x. What do we have in the first piece? A. How about the next piece? 4a. Don't forget about the 4. And the last piece. 4a. A plus 4a plus 4a makes 9a. Okay, let's go to the squares. All right, do we have any squares floating around anywhere? 4b at the end. Okay. Let's go to x's. Do we have any x's? Okay, so we have an x here. What would that be? 8b. So don't forget about the 4. It comes through. Anything over here? 4c. So we have 8b plus 4c. All right, how about constant terms? 2b. Anything else? Plus 4c. plus 4d. All right, so we plug it in, take our derivatives. Now we gather up. You know, it's our hunting gathering phase. Gather up our coefficients. And now the next thing is to say, hey, this thing we just found has to match this part over here. And the only way it can match is if the coefficients of the pieces match. So for example, here I have 18 attached to e to the x. Here I have 9a attached to e to the x. What's our conclusion about 9a? 9a has to be 18 for this to work. Here I see 8 attached to x squared. Here I see 4b attached to x squared. What needs to be true? 4b has to be 8. Here I see 8b plus 4c attached to x. Here I see... don't see an x. What does that tell us? 0. And here their constant term is 2b plus 4c plus 4d. And here the constant term is 0. So now we have a system of equations. 4 equations. 4 things we don't know. I think we can figure it out, though. Let's try it. The first equation says 9a equals 18. What does that let us conclude? Yeah, we're pretty good at that one. Next one says 4b equals 8. b equals 2. Wow, it's very 2-y so far. Okay. Next one should be slightly more interesting. 8b plus 4c equals 0. Can you do that? B equals negative 4? Let's see if we can do that. We'll just say it out loud. So, c. So 2 times 8, that's because we know b equals 2. So 2 times 8 makes 16 plus 4c equals 0. 4c equals minus 16. So c equals negative 4. All right. Last equation, we're pretty good. We're on a roll here. 2b plus 4c plus 4d equals 0. So what was that? D equals 3? Maybe. Let's check. 2 times 2 is 4. 4 times minus 4 is minus 16. And plus 4d equals 0. So 4 minus 16 is negative 12. Bring it across, that'd be positive 12. And 12 divided by 4 is 3. Ah, nice. Which says we know A, B, C, D. So we actually know Y sub P now. We're after the general form. So the last thing to do is to put it all together. Namely, our complementary solution and our particular solution. So we can say our Y, some constant, e to the minus 2x, some constant x, e to the minus 2x. And we have a, e to the x, so that's 2 e to the x, bx squared, 2x squared, cx is minus 4x, and then plus d is plus 3. And we're good. That's it. We have our answer. All right, well, that's the end of the method of undetermined coefficients. So we now transition to our next topic. And we start by a little throwback. Back to your algebra days. We're going to talk about Cramer's rule. All right, so what was Cramer's rule? Now, Cramer's rule is about solving a system of equations. And the kind of system of equations we just talked about where we have, multiple, like 4 equations, 4 unknowns, but they're all nice combinations. Linear equations is what we call it. And so Cramer's rule is this sort of shortcut method. Well, maybe not necessarily a shortcut in the number of steps, but it's sort of like saying, hey, here's a compact way to find the answer. So it says, suppose you have this pair of equations. So some constant x1, some constant x2 equals some number. So here they're a11, a12, and b1. The subscripts are just to say, where do the constants fit in? So you can think of the first subscript as saying, that says which equation. So that's the first equation, second equation. If there's a second subscript that says, well, where are you in that equation? Okay, so you have 2 equations, 2 unknowns. Now, this can be written in sort of a compact matrix form as a matrix A, where we group the coefficients X, where we group the things we're trying to solve for, and B, where we have the answers. Now, you might say, oh, boy, matrices. Do we need to know these? And the answer is yes, because this is the next 3.5 weeks of the class. So we really do want to know matrices. So spoiler alert, you want to know matrices. Now I can tell you're excited. That's good. I'm excited. We're all excited. So lots to look forward to. Okay, so now what's the punchline? So the punchline says, suppose we want to solve x1 and x2 in this particular set of equations. So what you do is you take downstairs, you take your matrix of coefficients A, take the determinant of that. So that's what these bars mean, the determinant of that matrix. And that's the same case for both x1 and x2. Now upstairs, here's the thing. If you think about what's going on, you should think about it as the first column is attached to the x1. See how you have A11, x1, A21, x1? So the first column is the x1 part. And it says, look, if you're solving for x1, take that column that was attached to the x1, replace it by the answers. So in this case, the b1, b2. If you want x2, you take the column that was attached to the x2, replace it by b1, b2. And then you take the determinants. And that will find the answer. Now this works for 2 by 2, it works for 3 by 3, 4 by 4, so forth and so on. I don't recommend doing this necessarily when you're solving your system of equations from a method of undetermined coefficients. Oftentimes it's much easier just to set it up and you'll see that things happen. But let's do a quick example. Let's use Cramer's rule to solve for x and y where we have it here. So I need some numbers. 13? All right, that's fine. What?
2.
I?
2. 26.
2. 26. 7. 3. 21. Okay. 13x plus 2y equals 26. 7x plus 3y equals 21. Now, would you like to make any of these negative? No? All right, we're all optimists here. Everything's positive. Great. So, if we're solving for x, well, the point is it's going to be a ratio of two determinants. And downstairs, the matrix that we're going to take is just these numbers here. 13, 2, 7, 3. Now, upstairs, we say, okay, x, that's the column here. We're going to replace the 13, 7 by 26, 21. So 26, 21, and the other column stays as is. So let's take these determinants. Okay. Determinant upstairs, what do you do? So remember, if you're taking a 2 by 2 determinant, that what you do is you're going to have the two diagonals. So there's this diagonal, is that plus or minus? Plus, and this diagonal, minus. Okay. So 26 times 3, 78. And that's plus. 21 times 2, 42. And we subtract. Downstairs, 13 times 3, 39. Subtract. 2 times 7, 14. Now we could clean this up if we wanted to. 78 subtract 42, also known as 36. 39 subtract 14, also known as 25. And we're done. 36 25ths. That wasn't so bad. Let's try y. Okay, so for y, same downstairs. And now, what's the first column going to be? 13, 7. What's the second column going to be? 26, 21. And now comes the pain. Now, the denominator doesn't change. It's still 25 because it's the same denominator. So we already did that computation. We don't have to do it again. 13 times 21 is, right, starts with the 2, followed by a 7, followed by a 3. Yeah, 273. Right. Good. You got it. All right. Great. Right? Because you can think of this as 20 times 13 is 260. And then there's one more 13. So that gets you to 273. Subtract 7 times 26.
182.
What?
Wait, I did it wrong. No,
What?
hold on, I'm sorry. I don't know what I'm
It should end with a 2. And it'll start with a 1.
182.
182.
Never mind. I
Okay.
doubt myself.
Good. We shouldn't doubt yourself. 273 subtracts 182. 91. 91 25ths. And we're done. We're done. Okay, so that's how you can use Cramer's rule. Now you're probably thinking, couldn't we have stopped here? Yeah. But, let's do it. Now you might say, what does this have to do with anything? Well, okay. I feel like I should probably hide what it has to do with something. We're going to talk about a new idea. So this is called variation of parameters. So this is related to the method of undetermined coefficients in that we're trying to find a particular solution. And what we do is we say, suppose, and we're going to be a very special case, second order, y double prime, p of xy prime, q of xy equals f of x. Now notice you don't have to have constant coefficients. So we'll let you have coefficients that vary. But suppose we have our differential equation and we have our two solutions to the homogeneous part. So y1 and y2 are solutions to the homogeneous part. And what we want to do is we want to find the particular solution. So the idea is, well, let's build off of the solutions to the homogeneous part to find the solution to the particular part. So we're going to make an assumption. Namely that our particular solution looks like u1 times y1 plus u2 times y2. Now, at this point you're thinking like, oh, this feels kind of like we have these coefficients and that we just have to figure them out. And we do. But here's the fun part. u1 is actually not just a number, it's a function. So it's not like we have to figure out coefficients. We got to figure out functions that make this work. u1 of x and u2 of x. Okay. So here's where we go. We say, all right, here's our solution. If we can figure out u1, u2, we win. So that's the game. How do we figure out u1, u2? So we take derivatives. Okay. So product rule. Derivative of u1 times y1, well, it'll be u1 prime y1, so the derivative of the first. And then u1 y1 prime, where we take the derivative of the second. You'll notice I've separated them slightly. So that's where the derivative of u1 y1 goes. Derivative of u2 y2, same process. It goes into two parts. Product rule. And then we say, this is getting kind of long. Let's make it easy on ourselves. And we're going to add another assumption. We're just going to say, look, this part right here, let's make it 0. Now you might say, that's a wonderful assumption. How many assumptions do we get? Well, how many assumptions do we get? What do you think? Yeah, people are saying 2 because you can see there's only 2 assumptions on the board. Of course, I've hidden stuff over here. But we only get 2 assumptions. Now, why do we get 2 assumptions? The answer is we have 2 things to play with, u1 and u2. When we have 2 things we can fiddle with, that says we get 2 assumptions to make. But as soon as I make a second assumption, we're done assuming things. Our hands are tied. We have to stick from there on out with what the conclusion tells us. So our two assumptions are we actually have a solution and that this particular combination is 0. Now, are there other assumptions that could have been made? The answer is yes, but we're going to follow this set of assumptions. Okay, so now we say, all right, we know how to take the first derivative, which is good because we need the first derivative. We've got to handle the second derivative. We can ignore this part because it's 0. So again, we do a product rule. U1 prime, Y1 prime, then U1, Y1 double prime. So that's the product rule. Goes to those two pieces. Product rule goes to those two pieces. Okay. So now we plug in. So we're going to plug in our particular solution into our differential equation. And we know it's a solution. So that says that our function f of x is the result of what happens when we plug in our particular solution. And now we just have to see where our pieces go. Well, this first part here translates very nicely. So that's where that piece went. And everything else, we do some gathering. So let's look at U1. There's a U1, Y1 double prime. That will show up here, U1, Y1 double prime. There's a U1, Y1 prime. That shows up U1, P of x, Y1 prime, because there's P of x multiplying here. And then there's a U1, Y1, and that shows up as the Q of x times Y1. What can be said about Y1 double prime plus P of x, Y1 prime plus Q of x, Y1? If you need a hint, it says it right underneath it. Yeah, it equals 0. Good. Why? Because it's homogeneous. That was our assumption. We said, hey, we have these two pieces which we know are 0. So that part goes away. That part goes away. So that says, lo and behold, we actually have from our second assumption, y1 u1 prime plus y2 u2 prime equals 0. And from plugging it in, we have that f of x is equal to that part. Everything else disappeared. y1 prime u1 prime, y2 prime u2 prime. Now, does this remind you of anything? It kind of reminds you of what we were just talking about. It's almost like there's a reason we talked about Cramer's rule. Because this is a system of equations. Two equations and two unknowns, where the unknowns are u1 prime, u2 prime. Now you might say, this feels weird, Steve. These aren't numbers, these are functions. Is this allowed? And the answer is, yes, it's okay. Because what happens is we're doing two things. We're multiplying and we're adding. And as long as you do that, it doesn't matter what the objects are. Numbers, functions, or something even more exotic. So we say this is perfectly set up for Cramer's rule. So we can solve for u1 prime. Downstairs, we have this piece, determinant of that. Upstairs, we replace the first column by 0 f of x. Well, of course, it's easy to take this determinant. You get 0. Subtract f of x times y2. That's how you get the upstairs. Now downstairs, this weird w. What's that? Wronskian, exactly. The Wronskian, making a comeback. Because that's how you find the Wronskian. You know, functions in the first row, derivatives in the second. Then take that determinant. So, lo and behold, we can solve for u1 prime. We can solve for u2 prime. Well, if I have u1 prime, how do I get u1? Integrate. How do I get u2? Integrate. And so, that means we can have a formula. A nice, simple formula. Here it is. So, for y double prime plus p of x, y prime plus q of x, y equals f of x, y1, y2, linearly independent solutions. Then the solution, and you look at it, it's like so obvious, it seems so, it's like the first thing you'd think of, right? Y is minus y1 of x integral y2 times f over the Wronskian. Because this part right here inside there, this is our u1 prime. y2 times this stuff, but this stuff inside here is really u2 prime. And that's what's happening here. Now, technically, I should say U1 prime involves the minus sign, but that's all right. And, well, we're out of time. So next time, we'll do some examples. All right. Have a great day.